Perfluoroalkoxy Alkane exhibits an impressive array of physicochemical properties that place it among the most robust materials known in polymer science. Structurally, PFA is derived from copolymerization of tetrafluoroethylene with perfluoroalkyl vinyl ethers, resulting in a semi-crystalline polymer with exceptional chemical and thermal stability. The defining characteristic of PFA lies in its unique substitution of hydrogen atoms with fluorine along the polymer backbone, akin to polytetrafluoroethylene, but with sidechain ether functionalities that bestow improved melt processability. This subtle structural variation introduces significant implications for both processing and final material performance, making PFA a material of choice for critical applications across semiconductor manufacturing, chemical processing, and analytical instrumentation. In this video, we will explore the chemistry, properties, processing behavior, and diverse industrial uses of PFA, alongside an overview of its limitations and emerging innovations. The synthesis of PFA involves the free radical copolymerization of TFE with perfluoroalkyl vinyl ether monomers, typically perfluoropropyl vinyl ether or perfluoromethyl vinyl ether. This copolymerization proceeds under high-pressure emulsion or suspension conditions in fluorinated solvents or aqueous systems stabilized with perfluorinated surfactants. The presence of alkoxy side chains introduces controlled branching and imparts thermoplastic behavior, differentiating PFA from highly crystalline PTFE, which cannot be melt processed. From a synthetic standpoint, controlling the molar ratio of vinyl ether comonomers is critical for tuning crystallinity, viscosity, and thermal properties. The resulting polymer chains exhibit a high degree of fluorination, with carbon-fluorine bonds dominating the backbone and side chains. These CF bonds confer exceptional resistance to thermal degradation, oxidative stress, and chemical attack by acids, bases, and organic solvents. Furthermore, the inclusion of ether groups creates small-scale flexibility in the polymer chain, reducing the melting point to approximately 310 degrees Celsius compared to 327 degrees Celsius for PTFE. Perfluoroalkoxy Alkane exhibits an impressive array of physicochemical properties that place it among the most robust materials known in polymer science. Thermally, PFA is stable up to 260 degrees Celsius in continuous service, with transient exposure tolerable up to 310 degrees Celsius. Its decomposition initiates only at elevated temperatures exceeding 400 degrees Celsius, yielding volatile fluorocarbons and HF. Mechanically, PFA offers moderate tensile strength and good elongation, typically exceeding 300%, although slightly lower than PTFE. What distinguishes PFA is its processability via standard melt extrusion or injection molding techniques, allowing it to be formed into complex geometries, something PTFE fails to accommodate due to its high crystalline nature and gel-like processing behavior. The chemical resistance of PFA remains virtually unmatched. It resists attack from almost all chemical reagents, including concentrated acids, alkalis, and oxidizing agents. Its surface energy is extremely low, typically around 1820 mmnm, contributing to its excellent non-stick and anti-fouling properties. Electrically, PFA exhibits a low dielectric constant, about 2.1, and a very low dissipation factor, rendering it highly suitable for wire insulation and components in high-frequency applications. Moreover, PFA is inherently flame retardant, classified as V0 in the UL 94 flammability test, and produces minimal toxic emissions upon combustion. Unlike PTFE, which requires sintering or paste extrusion, PFA is melt processable, allowing for a broad range of thermoplastic processing techniques. This includes extrusion, injection molding, compression molding, and blow molding, enabling the production of films, sheets, tubing, valves, and linings with remarkable uniformity and precision. Processing PFA, however, requires specialized equipment due to its high melting point and the need for corrosion-resistant tooling, often made of hastelloy or nickel alloys. Precise temperature control is crucial to avoid degradation, as thermal decomposition generates toxic byproducts including perfluoroisobutylene and hydrogen fluoride. Processing must also account for PFA's high melt viscosity and low surface energy, which can impact adhesion and welding. Surface activation techniques, such as plasma or sodium etching, are commonly used to enhance bonding with other materials. The unique performance profile of PFA renders it indispensable in high purity and high stress environments. In the semiconductor industry, PFA tubing and fittings are used extensively in ultra-pure chemical delivery systems, where metallic contamination is unacceptable. The material's inertness ensures that it does not leach ions or degrade over time, preserving process integrity. Similarly, in chemical processing plants, PFA-lined pipes and vessels handle aggressive reagents like hydrofluoric acid, nitric acid, and chlorinated solvents, where stainless steel or other engineering plastics would rapidly fail. In life sciences and analytical instrumentation, PFA's ultra-low extractables make it suitable for labware, sample containers, and analytical tubing used in trace-level contaminant detection. Its non-wettability and thermal stability further support its use in HPLC systems and microwave digestion vessels. In the electronics and aerospace sectors, PFA serves as an insulating material for high-performance wires and cables, operating under extreme thermal and dielectric stress. Its radiation resistance also allows it to be employed in nuclear settings and deep space applications. Lastly, the food and pharmaceutical industries benefit from PFA's FDA compliance and ease of sterilization, using it in fluid handling systems and bioreactor linings. When compared to other fluoropolymers such as PTFE, FEP, fluorinated ethylene propylene, and ETFE, ethylene tetrafluoroethylene, PFA balances high-temperature performance with processability. While PTFE surpasses all in terms of chemical inertness and dielectric performance, it lacks the thermoplastic nature that makes PFA favorable for complex parts. FEP, while melt-processable and chemically resistant, operates at a slightly lower temperature range than PFA and lacks its mechanical robustness. ETFE, though mechanically strong and more impact-resistant, sacrifices some chemical and thermal resistance. Hence, PFA stands as a high-end compromise, ideal where both high purity and structural integrity are non-negotiable. Despite its superior properties, PFA is not without limitations. Its cost remains high relative to conventional polymers and even other fluoropolymers due to the complexity of its monomer synthesis and polymerization processes. Furthermore, its mechanical strength and abrasion resistance, while acceptable, are lower than those of engineering thermoplastics such as PEEK or PPS. This restricts its use in load-bearing or high-wear applications unless reinforced. Additionally, processing challenges such as high melt viscosity and the requirement for corrosion-resistant equipment add to production complexity and cost. Environmental considerations are also gaining attention. Although PFA is chemically inert, its degradation products, persistence, and recyclability pose questions within the broader context of fluoropolymer sustainability. In conclusion, Perfluoroalkoxy Alkane, PFA, is a standout fluoropolymer whose combination of thermal endurance, chemical resistance, and processability underpins its vital role in modern materials science and engineering. Thank you for watching. For more on advanced polymer materials, stay tuned to our channel for future in-depth discussions.